Hi everyone. We are going to take a look at a couple of specific cases of periodic functions. Last day we talked about periodic functions being repeating patterns at regular intervals. Well, y equals sine theta and y equals cos theta are examples of periodic functions that are used to represent various situations. So we want to take a look at the graph, first of all, of y equals sine theta. And we could be using y equals sine x as well. X and theta are interchangeable as variables for an angle. So y equals sine theta, we are simply using the sine ratio for an angle and graphing those ratios. So theta or x is our angle. And if we punch into our calculators sine 0 or 0 sine, depending on your calculator which order you need to put that in, we find that we get an answer of 0. And I'm not sure if you've noticed, as we are doing the sine ratio for a really small angle, it is closer to 0. And as we get bigger and bigger, closer to 90 degrees, that ratio gets closer to 1. And that's exactly what we find as we punch these into a calculator. So rounding to 2 decimal places, sine 45 is 0.71, sine 90 is 1. And as we go into our obtuse angles, we notice that sine 135 is 0.71, sine 180 is 0. And if we put in now our bigger angles, we notice that we get a negative value for our sine ratio, and that's okay. We should be getting this. And noticing our pattern, and you can go through, I'm going through this fairly quickly, but you can go through and punch those values into your calculator and find those as well. And sine 360, we get back to 0. So we notice that there is a pattern here that 0 to 1, back to 0 to negative 1, and back to 0. And 360 and 0 make sense because they are in the same place. 360 is one rotation, so 0 and 360 should have the same sine ratio. And we notice if we keep going that our pattern continues. So we can still punch all of these into our calculators, and sorry, this should be sine of 720. And we can also do that if we look at our negative values. So sort of moving backwards into the negative angles, we find the same pattern. So sine of 0 is 0, then we have our negative 0.71, negative 1, negative 0.71, back to 0, etc. And again, I'm going through this fairly quickly, but you can check these in your calculator as well. The main thing we want to notice is that we have a very specific pattern, a regular pattern. So this is one cycle of our graph, which we will see as we graph this. So plotting our grid, we're going to look at and plot all of those points that we just came up with on our table of values. So we saw that from our table, we have our theta axis and we have our y-axis. We want to think about how we're going to plot these points. So for y, the biggest value that we had is 1. The smallest value that we had is negative 1. So we're going to use 0.5 as each of our y scale. So we're going to put 1 and negative 1. We know 1 was our maximum. -1 was our minimum, which we can fill in on the bottom here as well, our biggest and our lowest values for y. For theta, we're going to use 45 degrees on each scale on the horizontal axis or theta axis. Now, we don't have to label every single one of them, so every other is going to be 90. So we're just going to label every 6, sorry, that's not right. So if we go by 45s, every 4 should be 180. So 1, 2, 3, 4 is 180. 1, 2, 3, 4 is 360. We just want to do this so that we don't have too much of a cluttered axis here, but that we can see enough to plot easily. Okay, so it's important when we're plotting these that we make these clear and easily graphed. So plotting our points, we can start at 0, 0, and we know that at 45 we had 0.7, so it's going to be just below the middle of this one. 90 and 1, and we continue 180 and 0, and as we plot our points, again, we notice a very specific pattern. And we can see that our periodic function of y equals sine theta is taking shape here. We know that, and sorry, I messed this up a little bit here, but we have a nice smooth sine curve. And we also recognize that as we go backwards, that this pattern continues just the opposite way. And again, we're just plotting our points that we got on our table of values. So taking a look at our characteristics of our sine curve. And notice that we have arrows on both ends. This pattern continues in both directions as we get bigger angles, either positive or negative. So we've already talked about our y values, maximum being 1, minimum being -1. And we talked about that when we were calculating and using it for our triangles, that we should never have a sine ratio that is greater than 1 or smaller than -1. Looking at our y-intercept, we have a y-intercept of 0. Now for our x-intercepts or our zeros, where it's crossing the y-axis, where y is equal to 0, we know that it happens every 180 degrees. So at 0, 180, 360, 540, 720. So we can write this as n times 180. And n is going to be an integer. Okay, so we're not talking about 0.5, we're not talking about 0.7, we're talking about 0, 1, 2, 3, etc. So 0 times 180 is 0, 0 times 1 is 180, 2 times 180 is 360, 3 times 180 is 540, etc. It's crossing every 180 degrees. Our amplitude, or our difference between remember, amplitude is our maximum, subtract our minimum, divided by 2. So our amplitude here is 1, and that does make sense here as well, because we talked about amplitude is basically half the height of our graph, which is 1. And our period for a full cycle of our graph, we notice that we go from 0 to 180, and back to 0 where we start our new cycle in 360 degrees. Okay, so that's our graph of y equals sine theta, and your work for today is to go ahead and do the same thing with y equals cos theta. So you're going to use your calculator to find your values, again rounding to 2 decimal places, and you can plot your graph exactly like we did with this graph of y equals sine theta, and take a look at the characteristics there as well. Okay, and as always, let me know if you have any questions. Take care and have a great day.